Okay, hello everyone. Today our team want to present the topics. How fast does a tank drains for our calculus assignments? Okay, so this is our group member names. And first, let's start with the main questions, which is why the speed of tank drains is inconsistent. When a water tank drains, the water flow very fast at first, but as time goes on, the flow gradually slows down. This shows that the speed of draining is not constant. But why this happens? The main reason is that the water height in the tank decreases continuously over time. And since the water height affects the speed at which water exists, the flow rate changes as the tank empties. This leads us to the key questions. How can we calculate the rate at which a tank empties when the flow rate keeps changing over time? To answer this, we first need to understand the relationship between water height and water velocity at any given moments. Okay, to calculate the water speed at a specific height, we use Torricelli's laws that state the speed of a fluid flowing out of a small hole in the containers is the same as the speed of an object would gain if it fell freely from the surface of the fluids down to the level of the hole. In other words, the potential energy of waters at the surface is converted into kinetic energy as it exists in the holes. If we equate the potential energy and kinetic energy, we get the formula V is equal to square root 2gh. Here, V is the instantaneous velocities at a specific height, g is the gravity, and h is the height of the waters above the hole at that moment. This formula allows us to understand how velocity changes with water height, but it does not tell us how the height changes over time or how long it will take for the tank to empty completely. Now, how does this connect to calculus? As we just discussed, the height of waters changes continuously over time, and since velocity depends on height, the flow rates also change continuously. The formula square root 2gh gives us only the instantaneous velocities at a specific height. It does not account for the full process of draining. To model the entire draining process, including how the water height decreases over time, we need calculus. Using calculus, we can express the rate of change of water height as a function of time. This gives us a differential question that, when integrates, can calculate the water height at any given time and eventually the total time need for the tank to empty. In the next part, our team will show how this formula is applied to form the differential equations and how we can solve it to determine the total draining time.
Okay, I will explain the formula with calculus. So there are some variables that we need to pay attention. So the first one, the V small for velocity. V big is the volume of the water of the tank. A is equal to area of the tank. A small is for the area, but it's used for the whole of the tank. So where the waters will come up. H is the head of the water. HO is the head of the water, but in the initial condition. Okay, there one formula that I need to explain. So this Q is a flow rate. Flow rate is means that how many volume of water that will come out in 1 second. So equal to AV. AV is velocity from the Torricelli law. So, and also we can say equal to dV over dt. So the changes of the inside of the water in tank is equal to water inside the tank minus the water that come out. So if we derivative it, it becomes dv over dt, and also the volume of the water in the tank is constant, so it's become 0. And v out, we change it become the flow rate, so it's minus av. And v we put, and for the v we change it from the Torricelli law from become like this. So dv over dt equal to minus a root 2 gh. Okay. So the volume of the water of the tank is equal to area of the tank times h. It means that the h of the water. So dv over dt is equal to a dh over dt. So we derivative if both of side. So it's dv over dt. We change to into formula that we already get equal to hey dh over dt. So after that, we will integral it because we will want to know the condition, the initial condition of the Higgs. Because in here we need to search the function of Higgs. So it's become minus. We put the dt to the left, dh to the right. So after that, after we integrate it, we get this function. So want to know the c. We can say that this integral is for to know the initial condition of the Higgs. So we put Higgs equal to H0 when t equal to 0. So when it's haven't happening the draining of the water. So is c equal to 2 of root h c equal to 2 root h o. So it becomes this this equation. After that, the function of h become like this. So this is the function of waters of respect time. So how to know how long the tank is empty? So the tank is empty when the haze is equal to 0, when the waters already runs out. So haze, this the function of haze is equal to 0. So it's become like this. After that, the root of his h0 we put to the other side, become like this. After that, we erase it, so we already get the formula for the search the time when the tank is already empty.
Hi, now I'm going to talk about the example of question. We have a vertical cylindrical tank contains water and has the following data, which cross-sectional area of the tank A equals to 1 meter square, area of the hole at the bottom A equals to 0.01 meter square, initial water height H equals to 4 meter, gravitational acceleration G equals to 9.8 meter per second square. Now, we want to derive the differential equation describing the change in water height. Find the height of water as a function of time, ht. Determine the time required for the tank to be completely empty. So for the first question, dH over dt equals to negative A over A square root of 2gh. And we sub the value inside. We get negative 0.01 over 1 square root of 2gh. We get negative 0.01 square root of 2gh. For the second question, ht equals to square of square root initial height minus a over 2a square root of 2gt. And we sum the value inside. We get square of square root 4 minus 0.01 over 2 square root of 2 times 9.8t. And we get square of 2 minus 0.005 square root of 19.6t. And for the last question, t equals to 2a over a square root of initial height over 2g. And we sum the value inside. We get 2 times 1 over 0.01 square root of 4 over 2 times 9.8, and we get approximate 90.35 seconds. And thank you.
Now let's move on to the applications in daily life. What is the idea here? The idea of this concept is basically the rate of change, right? Which is a core concept in calculus. Now, let's see in what aspects are they used. First aspect is first aspect they are used is in water tanks and reservoirs, such as water tanks in houses, tanks on buildings, and water towers. Here, engineers need to know how long a tank will take to empty and whether water pressure will remain sufficient. Here, using calculus, engineers can predict the draining rate instead of guessing and ensure the tank does not empty too quickly, which could cause some problems. Another aspect this is used in is drainage and safety systems. For example, they're used in like bathtubs, sinks, and industrial tanks. If a tank drains too fast, the pipes may be damaged and overflow or pressure problems can occur. Calculus helps engineers design the size of the hole or pipe so the liquid drains at a safe and controlled rate. They're also used in fuel tanks and containers, which the same idea applies to them. Knowing the rate of change of liquid level is important to prevent leaks, avoid wasting fuel, and ensure safety. In everyday situation, we might have observed some of the examples of this concept. Maybe you have seen where when a bathtub is filled and when we drain it, it may seem fast at first, but then it will, as the water height become low, it will also drain slowly. Or maybe when we want to empty the water bottle will empty quicker when it's full. These are the real life example of changing rates which calculus explains using derivatives. So for the conclusion, all these examples depend on one idea, which is how a quantity changes with respect to time, which is exactly what the derivatives represent in calculus. Calculus here allows us to measure how fast something changes at an exact moment. Well, without calculus, we can only say the tank will empty in some time. We cannot say how fast it is draining at a specific height. But with calculus, we can model, predict, and control real systems for this. Thank you.